Hi, everybody. So today we're just going to talk about the SAT math section. This is going to be kind of going over some of the concepts we talked about last week. I think there were some technical issues with that. So covering, again, the Passport to Advanced Math portion of the SAT, kind of building on the concepts we talked about in the first section. These are just going to be more of those kind of pre-calc questions, more advanced algebra, dealing with polynomials and those kinds of concepts. And that's going to be what College Board is looking to test here is really your ability to work with concepts that are going to be tested in college level math courses, right? So this is going to be where I think a lot of students are going to find the most challenging questions, but we're going to go over today some of the types of questions you can expect to see and also some examples of those questions just to get you a better feel for what the section is going to look like. So with that being said, let's move over to the slide deck. And again, we're just dealing with two main things today. The first being the advanced algebra, and the second being test taking strategies. And what I've done with the advanced algebra is, Passport to Advanced Math is such a broad category of questions that, it can be hard to say, oh, what exactly does that mean? So what I've really done is identified a series of like kind of the subcategories of advanced algebra questions that you might see, going over the basic concepts that you'll want to know in order to have the skills necessary to answer those questions, and then from that point forward, doing the actual practice problems that will let you see exactly what kind of questions you'll end up seeing on the test day. So we'll start with polynomials and rewriting expressions. So this one, the real major math skill that you need to know here is simply how to manipulate polynomials when they're maybe not in their most expanded form, or maybe they're not all on one side. And so that's basically saying you can add, subtract, or multiply exponents of, terms of the same exponent. For example, x squared plus x squared is 2x squared, x squared minus x squared is 0, that kind of stuff. And so this is going to be one of the most straightforward kind of advanced math questions that you're going to be seeing on the SAT. And so typically they'll just present you a straightforward equation and then ask you to either manipulate the equation in some way or solve for some unknown variable. So let's take a look at this question right here. So we have x squared plus bx minus 2 times x plus 3 equals x cubed plus 6x squared plus 7x minus 6. So in this equation, if the equation above b is a constant, if the equation is true for all values of x, what is the value of b? So we want to pause here and say, okay, so what's the basic strategy I'm going to take when it comes to this question, right? And taking a look at this question, it seems fairly simple that we should just be multiplying out the terms on the left side of the equation and then kind of trying to get all the terms on one side, right? Another strategy we want to take is say, after we multiply out this equation, we know that because there's an equal sign, the terms on the left side must equal the terms on the right side, and therefore the coefficients must also be equal. So why don't we get started with the actual kind of mathematical portion, and that's just multiplying out the left side of the equation, right? So we have x squared plus bx minus 2 times x plus 3. So that's going to multiply out to something like, whoops, let's get the pen on. So we have x squared, we got x cubed plus bx squared minus 2x plus 3x squared plus 3bx minus 6, right? And so that's going to be equal to what we have on the right side. And basically, with these two equations being equivalent, we want to be able to say, okay, how can we simplify this, right? So putting together the like terms here, bx squared and 3x squared both are coefficients of x squared, so we can add that together. So we have x cubed plus, let me see if I can write this with a little bit more space, x cubed plus b plus 3x squared. And then what else do we have here? So we have negative 2 and 3b as our other two coefficients for x. And so we can put those together as well. We get 3b minus 2 x and then looks like everything else is going to be about the same, except -6. And that equals, on the right side, we've done nothing with the right side of the equation so far, x cubed plus 6x squared plus 7x minus 6. And that's straight brought down from the right side over here in the original equation. So now we can look at these two equations and say, okay, what's the next step, right? And we know, again, because the equal sign, the coefficients must be the same, the variables must be the same. And we have this format where we see that a lot of the things are the same, right? We have x cubed here, we have -6 here, we have x cubed here, -6 here. So we know that basically this coefficient must equal 6. I'm not sure why I wrote an extra plus sign here. And then 3b minus 2 must equal 7. So you can solve either of those equations, right? You get b plus 3 equals 6. That means b equals 3. We could solve the other one. 3b minus 2 equals 7. 3b equals 9. B equals 3. Either of these are going to work, but our final answer is going to be 3, right? So hopefully this makes sense, kind of seeing that, it's just a little bit more complicated than the kind of basic linear algebra we were working with in the Heart of Algebra section of the SAT. We're multiplying out polynomials. We're having to navigate between, coefficients of two different variables versus a constant coefficient. But, at the end of the day, like the process is still going to be fairly similar and fairly straightforward. So hopefully that makes sense to everybody and is kind of a clear-cut approach to this type of question. So we can take another look at other types of questions. And so for this one here, this is kind of testing more so our comfortability with shortcuts and kind of very fundamental formulas when we're dealing with polynomials. So the question says, which of the following is equivalent to 16 times s to the power of 4 minus 4 times t squared, right? And so what we're dealing with here is saying, okay, basically we can look at the answer choices and say we're trying to simplify this question here, right? And the question is, how do we go about simplifying this question? So, and we're going to cover this in a few slides as well, but there's some basic polynomial rules, right, that are going to regulate what we're doing with this question. The one we're really going to want to think about when we see this is, a squared minus b squared equals a plus b times a minus b, right? And so this is what we call the difference of squares rule. And basically, anytime you can put a equation into this a squared minus b squared format, you can simplify it into the factored form a plus b times a minus b. And so this is going to be something that you'll actually probably see fairly often on the math SAT section, at least when it comes to advanced polynomials and algebra. So we can try and apply this to our equation here. And so at first glance, we might say, well, this doesn't seem to apply here. We have, s to the power of 4, not s to the power of 2, and we have terms here. And so what we want to say is, as long as we can put it into the right format, a squared minus b squared, then it should be okay, because a does not necessarily represent a single variable, right? It represents, any term that you can place into this format. So what way can we rewrite 16 times s to the power of 4 minus 4t squared into a squared minus b squared? When we look at this question, it should be fairly obvious on first glance that 16 and 4 are perfect squares, right? So we know that this is kind of hinting towards the direction we're supposed to take with this. So let's take a look. So we could rewrite this as, instead of 16s to the power of 4, we write 4s squared again, minus, and then do 2t squared. And all of a sudden, now we see we have it in the a squared minus b squared form, right? We have 4s squared as a and 2t as b. And if we square these out, it would be 16s to the power of 4 and 4t squared, which is exactly what we have in the original equation. So we can see these are equivalent. And now when we've put it in this form, we know that the rule is going to apply for difference in squares. And that's going to give us something that looks like this, right? 4s squared plus 2t times 4s squared minus 2t, right? And so that seems pretty straightforward here, right? And so we go to our answer choices and say, hey, wait a second, like the answer we got does not match any of the answer choices. Does that mean we did something wrong? No, it probably means that we didn't simplify fully, right? So is there anything we can do with these terms to make it simplify even more? So maybe we go to 4s squared minus 2t, and we say, is this a difference in squares? And no, it's not, right? Because t is only to the power of 1, it's not squared. It's really hard to put that into a difference of squares format. So what else could we do? Well, we see that, in this first term, 4s squared plus 2t, both terms in the parentheses are multiples of 2. So we can factor out 2 here. That's going to give us 2 times 4, 2 times 2 squared plus t, right? And we can do the same thing with the second parentheses, right? Also factor out another 2. So we get 2 times 2s squared minus t. And I'll put that together. We're going to get something along the lines of 4 times 2s squared plus t times 2s squared minus t. And that, if we go back to revisit the equations, should be very similar to one of the answer choices we have, and that's going to be answer choice C, right? 4 times 2s squared minus t times 2s squared plus t. That's going to be the same as what we got, and that will be our correct answer. You can see here, this was a test of the rewriting expressions form. How do we rewrite this into a different format? And again, we'll be talking in a few slides about difference in squares and some other factoring methods that are going to allow you to kind of simplify or rewrite, these polynomials into other forms. But hopefully this process made sense. And, difference in squares is not something that's going to be given to you on the formula sheet, but it's something I would highly, highly, highly recommend that you guys have memorized or have in your toolkit to use in situations where you look at a question and you say, these are perfect squares. This is a situation where I would want to use this shortcut. Okay. So the next question then is going to be kind of more of a simple question. It says, which expression is equivalent to xy squared plus 2xy squared plus 3xy? So it's not, a conventional polynomial. It's got two different variables. What are we really being tested on here? It's, again, simply saying, do you know when you're allowed to combine terms? Do you know when you're allowed to simplify further? So if we look at this question here, we can say, okay, well, can we factor stuff out? Maybe, but none of the answer choices are really factoring anything. Can we combine like terms? Xy squared is the first term, 2xy squared is the second term. They both are, coefficients of xy squared, so those can be combined, so we can get 3xy squared. Can we do anything with 3xy? Probably not. Like, we could maybe simplify this by factoring out, but none of the answer choices are asking us to do that. We can compare it to the answer choices here. And we're going to get b is exactly matched to what we have. And so this one, again, is not going to be very complicated. As we can see, it didn't take a lot of different steps for us to get to the right answer. But really just making sure that we're noticing the like terms, knowing that, just because there's two variables in this polynomial does not mean this is a hard question. And so just, seeing that there's a lot of different, there's a range of difficulty of questions when it comes to the SAT. And this one is going to be on that easier range, and that's going to be one that you want to make sure you get. Okay, so hopefully those questions kind of cover the basics of what we call polynomials and rewriting your expressions, right? So in that sense, we can move on to the next category of questions, and that's really going to be quadratic functions. And this is going to be one of those meaty sections of the SAT where you're dealing with a lot of different tools that you need to really be able to use. And it's also just going to be a concept that the SAT the College Board test makers are really going to focus on, because this is going to be a basis for a lot of more advanced math questions, right? So we'll read this little excerpt from College Board's website. They say, the SAT math test may ask you to solve a quadratic equation. Be prepared to use the appropriate method. Practice using the various methods below until you're comfortable with all of them. So below we have method number 1, factoring. Number 2, completing the square. Number 3, using the quadratic formula. And number 4, using a calculator. And so I would say these are your 4 methods, definitely. And they are also in the order of most efficient to least efficient, in that you should probably have factoring be your default approach for most questions. And if not, then move on to completing the square. And if not that, then quadratic formula. And last resort, calculator. It's really important to be comfortable with all of these tools, because some questions are going to be more well suited to certain methods of solving than other questions. And that's something that's really important to understand. And therefore, is it possible to solve a factoring-based question with a calculator? Absolutely. And is it possible to solve, a quadratic formula, uh, method with factoring? Sure. But, with some of these methods, you're going to see that, it's going to take you a lot longer to do one way than another way. And because this is a time test, the more appropriately you can pick the right method for the question at hand, the more time you're going to save and the more time you're going to be able to spend on other questions, right? So we want to be comfortable with all of these. That being said, again, all four of these methods, if applied to a question, will get you the end result and will get you the right answer. It's just a question of how long will it take you to get there. Okay, so factoring is going to be that first method, and there's a couple different ways and a couple different little shortcuts that you can take. So this is going to depend maybe on how you were taught in school, but there are a few basic rules that are conventionally followed, right? So we have what's called a sum product pattern. And so that's where you have a polynomial where it's given in the form x squared plus bx plus c. So you see here that a is not here. A is just 1, so there's no coefficient for the x squared. B represents the coefficient for this x term, and C is the constant at the end, right? So those are variables that stand in for numbers. And so basically the rule here is that if you want to factor this into its base form, then factors of C add up to B, right? So if you take the numbers that multiply together will equal C, those numbers should add up to B, and those will be your factors. And so I think, that's complicated to think about abstractly. Why don't we just take a look at the practice question that we have. So we have x squared plus 7x plus 12. And so again, the sum product pattern is asking us, or the question we should be asking is, what are the factors of 12 that when added together give us 7, right? So we can do a lot. We can do 1 times 12 is 12. Added together, that's 13. That's not right. 2 times 6 added together is 8. That's not right. 3 times 4 is 12. Plus added together is 7. And that's going to be right. And so that's why our last answer, sorry, our final answer is going to be x plus 3 times x plus 4, because we have 3 and 4 being the factors of 12 that add up to 7. Hopefully that makes sense. So the next method it's not really a separate method. It's just you're adding another dimension to the sum product pattern. And it's basically called the grouping method, where instead of having x squared plus bx plus c, you have ax squared plus bx plus c. So now a is no longer just 1, it's actual coefficient. And that means that you're not just looking for factors of c that add up to b, but factors of a times c that add up to b. And that is going to be, again, seen in this question here. And I think the easiest way to, I mean, this is the way that I was taught, is that if you have, this setup, and you can use this for sum product pattern as well, you can draw it into a kind of a square format, right? So let's say the first, with like points, these, these 4 points, right? So in these 2 points right here, we're going to do the factors of the x squared, so factors of a. So with 2 being, with a equal to 2, we know that our factors are going to be 1 and 2 no matter what, right? So we can just write that here. So 1 and 2. And then the other 2 points are going to be our factors of c, and that's going to be, for 3, it's 1 and 3, right? And so basically, we want to put in a couple, easy trial errors, and we can, try and see if we can get this to add up to our b variable, which is 7. So we're going to cross multiply. We're going to do 1 times 3 is equal to 3, and then 1 times 2 is equal to 2. 3 plus 2 is 5, right? So 5 is not equal to 7, right? And so that's not going to be the right kind of split for us. We can try this again. We have 1 and 2, and then instead of doing 1 and 3 this way, we can try and flip it. So 3 and 1. And we can cross multiply again. So 1 times 1 is 1, 2 times 3 is 6, 6 plus 1 is 7. That's going to be our right answer. And so what we can do from this is kind of easily see, and this is why this format is easy to use, we can just take the coefficients here and make these our terms. So if the first coefficient is 1 and the second coefficient is 3, then our first term is 1 times x, which is just 1, plus 3. And then our second term is 2 times x, right? 2 and 1, 2 times x plus 1. And that should be our final answer, right? And we see here that is indeed the case. Sorry. Whoops. We are, in fact, dealing with this case, right? So That's kind of the method that I use when I'm doing these factoring problems. So again, if this is something that is not the most intuitive for you, or is not something that you're very comfortable with, I would just recommend going online, finding a lot of practice questions, and just factoring a lot. And the practice and the process of going through the solving mechanism is going to make you a lot more comfortable with that approach to solving these questions, right? But hopefully this method makes sense and kind of allows you to see how you're supposed to be dealing with any of these polynomials, whether it be x squared plus bx plus c or ax squared plus bx plus c. Okay. Another kind of these two are kind of more shortcuts. We talked about difference of squares already. If the expression represents a difference of squares, aka a squared minus b squared, then you can rewrite it as a minus b times x, a plus b, right? So we can see that here. And then the other one that we haven't talked about yet is the perfect square trinomials. And so that's basically where if the first and last term, so that's x squared and 25 here, are perfect squares, and the middle term is twice the product of their square roots. So square root of x squared is x, square root of 25 is 5, 5 times x is 5x, times 2 is 10x. So this is a middle term that is twice the product of the square roots of the first and last term. Then you can simplify that to be x plus 5 squared, right? And so that's, again, this is just a shortcut where the two factors are the same, and therefore they can be combined into one parentheses squared, right? And so that term in this simplification is not necessary to know, I would say. You could do the same method, like if we wanted to do our little square method, the factors of 1 are 1 and 1, factors of 25 are 5 and 5, that add up to 10. 1 times 5 is 5, 1 times 5 is 5, that adds together to 10. And so we would have x plus 5 times x plus 5, which equals x plus 5 squared, right? And so, we get to the same answer no matter what. This is just maybe something, if you recognize it, it'll allow you to, use that shortcut a little bit more efficiently. Hopefully that makes sense. And again, these are less so required to know, and more so shortcuts that you can use when you have questions that are set up in ways that it can save you some time. Again, difference of squares, if we think about it, what it really means for a difference of squares is simply that b equals to 0, right? And so that's why when we do these cross multiplying for this, it would be like 1, 1, negative 3, 3. So 1 times 3 is 3, and 1 times negative 3 is negative 3. Added together, it's 0. And that's why it has this different look. And that's, again, just something that you would still be able to do if you just use a conventional factoring approach as well. Okay, so hopefully that makes sense to you guys. And if not, definitely seek out some practice questions and make sure that's something that you're very strong on, because I do think that factoring is the best method for most of these questions. It's going to be your preferred method. And if you can be comfortable with factoring, you're going to be very well equipped for the quadratic type of questions on the SAT. Okay, and then we also have other approach, which is going to be quadratic functions. Sorry, the quadratic equation. And this is something you guys will have seen in class as well. It's basically a equation that will give you the roots for any polynomial where you know a, b, and c, right? And so if we think about a conventional polynomial as of the format ax squared plus bx plus c, right? Y equals ax squared plus b plus c, and we want the factors. The quadratic equation goes negative b plus or minus the square root of b squared minus 4ac divided by 2a, right? That's quite a mouthful, but what we're basically doing is we're plugging in a, b, and c into the different portions of the equation and kind of solving, right, and simplifying. All quadratic functions in every circumstance are going to have a, b, and c as constants. So these are all going to be numbers, and therefore you're going to know you're going to get a numerical answer for this equation. Because there are two factors, that's why we have the plus or minus sign. There's going to be one factor that's going to be negative b plus this term over here on the right, and there's going to be another one that's negative b minus that term on the right, and that's going to be this our two function or two answers. Quadratic function is going to be a little bit more time consuming. You shouldn't again be using quadratic equations as your default solution. It's only in situations where factoring is going to look too messy or maybe not even possible without a calculator that we would want to use the quadratic equation. And a lot of times questions that are intended to be solved using the quadratic equation are going to give you a sort of hint. And sometimes that means like the answer choices are going to be in a plus or minus format. And that's going to make it very simple or very, very straightforward that this is going to be a quadratic equation solution. And that's just something you want to keep an eye on. So again, be comfortable with this. I don't believe this is provided to you on your answer sheet. So this is something you will have to memorize. And so just know that this is a tool that you have when it comes to quadratic formulas as well. So that's basically. Oh, and then something I didn't cover is calculators. Basically, you can plug in any equation of the format y equals ax squared plus bx plus c. You can plug any equation of that format into your calculator and graph it. And when you graph those functions, you can look at the zeros on the graph, which are essentially where the graph intersects the x-axis, and those will be your quadratic functions as well, or not quadratic functions. Those will be your zeros or roots as well. Again, would not recommend that being your default approach to these questions. First and foremost, it's not always possible to plug into a calculator. You might be doing a quadratic question on a non-calculator section, so you won't be allowed to use a calculator. So having a default calculator solution is not going to benefit you when it comes to those non-calculator sections. Second, punching into your calculator is going to be time consuming. It's, sometimes the zeros are not very perfect if they're designed to be solved by a quadratic format. Sometimes, it's not, it's always because a calculator solution will always give you a decimal answer. Maybe the answer is going to be in fractions, or it's going to be in a plus or minus format. So there's a lot of reasons why calculator, solving is not going to be your preferred method. And at least in my experience, I almost never see a question where the preferred method is to solve with a calculator. It's always when there's some sort of other format that makes it a little bit less likely for calculator solving to be right, and therefore you would use a alternative method to solve that question. So again, keep in mind calculator, at the end of the day, if you can't solve it by the other methods, then feel free to use your calculator, and that's going to give you the right answer as well. So know that's something you can do, but don't go in thinking that's what you're going to do for every single question. Okay, so now we'll take a look at the practice questions we have for quadratics. So we have here, if x is greater than 0 and 2x squared plus 3x minus 2 is equal to 0, what is the value of x? And so we are basically looking at a factoring approach, right? So in what way can we basically simplify or factor this polynomial on the left so that we can find the roots which make this equal to 0? So taking our variables, our factors of a, which is 2, we know it's only possible that the factors of 2 are 1 and 2. And therefore, we are looking at the factors of c, which are is negative 2. So we know we can have 1 and 2 as well. And we also know that one of those variables is going to be negative for the two factors to multiply together be equal to negative 2. And then we want the cross-multiplied products of this square to be equal to 3. So let's take a look at some possible answers. So we can do 1 and 2 here. Maybe you want to do like something like this. 2 times negative 1 is 0. Sorry, 2 times negative 1 is negative 2. 1 times 2 is 2. Add together, that's 0. That's not going to be right. Let's try another one. 1, 2, 2, 1. Let's make this negative. 1 times 1 is 1. 2 times negative 2 is negative 4. Added together, that's negative 4 plus 1 is negative 3. But we want positive 3, so that's not going to be right. But if we just flip if we flip the negative signs, right, then we might get the right answer here. Instead of negative 2, we'll do negative 1. So 1 times negative 1 is negative 1. 2 times 2 is 4. 4 plus negative 1 is 3. And therefore, this is going to be our right answer. And so we can take it from here. So if 1 and 2 is our top row, then we have x plus 2, and then 2 and negative 1 is our bottom row. We have 2x minus 1, and therefore that equals 0, right? And in this sense, we know that we have two zeros here wherever x plus 2 equals 0. So if x plus 2 equals 0, then x equals negative 2, and then 2x minus 1 is equal to 0. Then we get 2x minus 1 equals 0, 2x equals 1, x equals 1/2. And so this seems to be a gridding question. We have two answers. How is that possible? We want to go back to the root and remember we are given the assumption that x is greater than 0. If x is greater than 0, that means it cannot be negative 2. Therefore, it has to be 1/2. Therefore, x equals 1/2 is going to be the correct answer for this question. So hopefully the entire process makes sense. Again, we chose to use factoring for this approach. That's going to be the fastest method. A lot of these calculations actually, if you become very comfortable with it, you'll be able to do in your head, and therefore will take even less time. And so, and then the other takeaway from here is, even though this is a very straightforward question, we want to remember, there might be extra information given to us in the question. We don't want to go ahead and just assume oh, I see an equation, let me just solve it. That's the right answer. If we had failed to look at taking a look at x must be greater than 0, then maybe we would have picked negative 2 as the right answer. Or if there's a multiple choice, it's possible that maybe one of the choices was negative 2 and 1/2 rather than just 1/2, right? And so we didn't want to have to actually mistakenly pick this one because that would have been wrong. So just keeping those ideas in mind. Okay, so taking a look at the next question. So here we have another equation that's given to us. It's not given to us in our conventional quadratic form, ax squared plus bx plus c. But we'll see very soon why this is a quadratic question. So we have x minus 12 is equal to the square root of x plus 44. What are all possible solutions to the given equation? The first thing you want to deal with is, because we're not going to, on the SAT, we're not going to know if this is categorized as a quadratic question. So we'll say, okay, well, is there any way I can simplify this without squaring both sides? Because squaring both sides is going to make this a lot more messy. And so is there any way, for example, I can take a term out of x plus 44, bring it out of the square root and try to get rid of the square root without squaring? The answer is no. X plus 44 is a pretty messy, unworkable term. We're not going to be able to get anything out of that. And so we're basically left with, okay, we got to square both sides, right? So let's do that. So we get x minus 12 squared is equal to x plus 44. X minus 12 squared equal to basically x plus 44 because the square root and the square cancel out. What's going to be x minus 12 squared simplified? That's going to be x squared minus 20. Oops. X squared minus 24x plus 144 equals to x plus 44. And then, as always, we want to get all of our terms onto one side. We can subtract x from both sides. That's x squared minus 25x. And then we can also subtract 44 from both sides, which is actually a pretty clean subtraction. 144 minus 44 equal to 100. Whoops, sorry. Plus 100, and that's equal to 0. We've subtracted both x and 44 from both sides. And so this is going to be our end quadratic form, and this is, again, much more simply a quadratic function. And then we can say, okay, how do we simplify this so that we can find the roots? So luckily, again, our a is equal to 0, so we just have 1, 1. And then we want to find basically roots of 100 that add up to negative 25. And so because 100 is positive, and negative 25 is negative, we know that the roots on this side must both be negative, right? Because two negative roots are going to add up to, multiply together equal to 100, a positive number, but two negative numbers added together will give us a negative number. So taking a look at this, the first number that comes to mind is 10 and 10. So does negative 10 and negative 10 work? 1 times negative 10 is negative 10. 1 times negative 10 is negative 10. Add together is negative 20. We want negative 25, so that's not going to work. What's another one? Maybe 4 times 25 Again, that's negative 29, not going to work. So in our head, we might say, what are some other options we have here? Maybe 5 and 20. And so we have negative 5, negative 20. 1 times negative 20 is negative 20. 1 times negative 5 is negative 5. Add that together, you get negative 25. So that's going to be our factored form, right? So we're going to get x minus 5 times x minus 20, and that's equal to 0. And then we get our two zeros, x equals 5 and x equals 20. And so some of you might say, okay, well, we're done then. We have our two factors, 5 and 20, and that's answer choice D. Maybe D is our right answer. We'll pick that and move on. But we have to remember that we didn't start with this pretty polynomial x squared minus 25x plus 100, right? We started with x minus 12 is equal to x plus 44 to the power of 1/2 or square rooted. In that sense, we have to go back and basically plug in our factors in order to make sure that both of them are going to work. Because of the square root, we know that squaring both sides might mess up something in terms of what's allowed and what's not allowed in terms of negative numbers as outputs of the roots. So plugging in, we can do 5 first. So we'll do every time we see x, we plug in 5. So 5 minus 12 is equal to the square root of 5 plus 44, and that's negative 7 is equal to the square root of 49 equal to 7. Negative 7 equals to 7, well, we know that's not the case. Therefore, 5 actually does not work as a solution in our original equation. So let's try our other root. 20 minus 12 is equal to square root 20 plus 44 equal to square root 64 equal to 8. 20 minus 12 is also equal to 8, so 8 equals 8. This checks out, and we know that x equals 20 is going to be our final answer. And that's going to be answer choice B. Hopefully that makes sense. Again, the key takeaway from this is, okay, first of all, there's a possibility that questions we might not expect to be quadratic questions will evolve into a quadratic equation. And the second thing is, always remember what you're dealing with. You're not dealing with your modified equation. You want to deal with the original equation, and especially if you're squaring both sides or dealing with radicals, you have to be careful and you have to double check your answers to make sure that they work with your original equation, not just your modified one. So that's a good catch. I think a good example of one where you get two roots, but only one of them actually works in our original equation, and that means the answer choice is going to be B. Okay, so hopefully that makes sense. We're going to take a look at this question now. What are the solutions to the equation x squared minus 3 equals x? And so what we can first do here is we can get all the terms on one side, set everything equal to 0. X squared minus x minus 3 equals 0. And then the next thing we can do is take a look at, just off first glance, what approach or tool that we have used is going to be the best suited for this question. And taking a look at these answer choices, we can see that they're all in this very unique format, right? They all have a constant plus or minus a radical on the right side divided by a constant. This is, giving us very, very strong signals that the approach that we're going to want to use is the quadratic equation approach, right? And, just to confirm, maybe you want to try factoring in your head, is there any factors of -3 that when added together equal -1? The answer is no, it's not possible. And so in that sense, we're going to basically say, yeah, let's settle on quadratic equation as our fundamental approach to this. So remembering what we have as a quadratic equation, we had x equals -b plus or minus b squared minus 4ac. So we have -b plus or minus the square root of b squared minus 4ac divided by 2a. Whoops. Right, and so we want to identify, what are the factors that we're dealing with here. So here we have a is equal to 1, b is equal to -1, and c is equal to -3. And we just plug that in, right? So -1, negative b is equal to -1 plus or minus square root b squared, -1 squared is 1, minus 4 times 1 times negative 3. And we want to divide that by 2 times 1. And then we can simplify. So we get negative times negative 1, so positive 1, plus or minus square root 1. 4 times 1 is 4, times negative 3 is negative 12, minus negative 12 is plus 12, so 13, so 1 plus 12, divided by 2 times 1 is 2, and our final answer is 1 plus or minus square root 13 divided by 2. And we can go ahead and find the right answer choice that matches our question, that matches our outcome, and that's going to be answer choice D, 1 plus or minus square root of 13 divided by 2, 1 plus or minus square root of 13 divided by 2. And that's going to be our answer for this question. Again, note that, we wanted to start off by rewriting a quadratic into a conventional form, ax squared minus bx plus bx plus c. And then we wanted to take hints, right? The test makers were kind enough to give us a question where all the answer choices are in the quadratic form. And in that sense, we basically knew that this is going to be the way we needed to solve this question. Now keep in mind, like we said before, this is a good example where could you plug this equation into your calculator, x squared minus x minus 3, and find the zeros by looking at the intersections with the x-axis? Yeah, that's possible, but that would give you all the decimals. It would give you 1 plus square root of 13 divided by 2, and then 1 minus square root of 13 divided by 2, and you'd have to convert that back over here to say which one of these fractions is going to give us those two zeros. That's a whole lot of hassle. Whereas if we use the appropriate approach, which is the quadratic equation, then we wouldn't have to deal with that, and we would just be able to do this very simple plug and chug approach and get the right answer. So again, another example of how using the appropriate method to answer the question is going to save you a lot of time and going to make your life a lot easier on the test. Okay, so let's take a look at this question here. What is the sum of the solutions of 2x minus 1 squared equals to x plus 1 squared? Sorry, x plus 2 squared. So taking a look at this question, we have several different approaches we could take. Now, I think some of us might, and myself included when I was doing the SAT, might just look at an equation like this and be like, all right, time to grind this out. We're gonna, simplify everything, multiply it all out, get everything onto one side, and then solve. And that's gonna be our equation and our solution. Another thing is, sometimes these questions, because this process will take a long time. Another solution is to just say, okay, well, if we know that these two terms are equal, we know that they're both raised to the second exponent, then we know that 2x minus 1 and x plus 2 must either be equivalent or be equivalent to the negative version of each other, right? So it's either 2x minus 1 is equal to x plus 2 or 2x minus 1 is equal to negative x minus 2, right? Because we know that when squared, negative numbers become positive and positive numbers remain positive, and therefore those are the only two situations in which this this equation would be allowed. And so that's going to allow us to kind of get rid of get rid of the exponents and just deal with the roots and say, okay, well, we know this root. One possible solution is 2x minus 1 is equal to x plus 2. This is just a linear equation, right? We can simplify by getting x onto one side, and then we get x equals 3 by subtracting x from both sides and adding 1 to both sides. We can do the other version of this where 2x minus 1 is equal to the negative version of the x plus 2. So we get negative x minus 2. We can simplify it again. We get 3x equal to negative 1. And we get x equal to negative 1/3. Right? And that's going to be our two answers and our two roots. And we can see here, we didn't have to go through any of the polynomial or quadratic simplification, right? We could bypass all that by noticing like the specific setup of this question and say, okay, well, we can work with this. We don't have to do a quadratic to solve this question, right? You could also say, why don't we just square root both sides, and then therefore you don't have to deal with the polynomials and all that. Okay, so the correct answer here is going to be 3 plus 1/3, so 8/3. right? And so that's going to be our solution. X equals 3 um, plus negative 1/3 is equal to 8/3, right? And so again, some of you, we want to be careful when we're approaching these questions, not to just get sucked into this mindset of, every equation is just a grind of, let me do the entire process, let me go through the entire, the whole motion of solving this question just to chug it out, when there are simpler ways that we can solve this. Now, is it the case that we could, solve this, by doing the quadratic form and factoring that way and dealing with that? Yeah, that's absolutely going to work. And we can go through that process here just in case, I think some of you might not have seen that this is a problem that we could have solved without going through that entire process. But we'll see that we can get to the same solution, but just watch how long this is going to take us if we don't do the fully simplified, if we don't do the shortcut or abbreviated version. So we have 2x minus 1 squared on this side. That's going to simplify us to 4x squared minus 4x plus 1. The next thing we have on the left side is going to be x squared plus 4x plus 4. We have x squared on both sides. We subtract, so we get 3x squared. 4x is on both sides. Minus 4x on both sides, we get negative 8x. And then minus 4 on both sides is going to give us negative 3, and that's going to give us 0 on this side. I want to say, what are the factors that are going to give us, how do we factor this basically into its root forms? We can take the factors of a, which is going to be 1 and 3, right? Again, thankfully, there's not multiple different factors of 3. On the other side, we have the same thing, also 1 and 3. You can write it this way, and we know that one of these has to be negative. The cross-multiplied roots must add up to negative 8. So taking a look at this equation, we have 1 times 1 is 1, 3 times negative 3 is negative 9, negative 9 plus 1 is negative 8, and this is going to be the right, this is going to be the right roots for us to take, right? So we have x minus 3 times 3x plus 1 equal to 0. X equals 3, and then 3x plus 1 equals 0. We can solve that. 3x equals negative 1, x equals negative 1/3. So we can see we got the same roots, 3 and negative 3 added together. 3 plus negative 1/3 equal to 8/3. We got the same answer at the end of the day. We just had to go through a lot more steps, right? We had to, multiple, we did the exponents on both sides. We had to simplify and get everything onto one side. We had to factor again. We had to solve for zeros. A whole lot of things that we didn't have to do at all when it came to doing the shortcut version of just 2x minus 1 is equal to x plus 2, or 2x minus 1 is equal to negative x minus 2, right? That's going to be a lot easier. So we want to just keep that in mind, that there are, ways in which you can bypass having to do the more complicated steps. Both approaches will yield you the same solutions. It's just one is going to take you a lot longer. Okay, and then the last quadratic question we have here. And this question here is really saying, can we apply our knowledge of what the quadratic form looks like, and also our ability to manipulate variables to basically translate a word problem into a quadratic equation, right? And so we can take a look at this here. And so this is going to be a little bit more tricky for some of us, because this is not straightforward math, right? This is not like, here's an equation, solve it. This is, here's a situation, a context. Put together a equation that represents the situation. And that's going to be a little bit more challenging, and that's something that College Board has very recently started to focus on in the types of questions that they're asking. So we can read it through here. A car is traveling at x feet per second. The driver sees a red light ahead, and after 1.5 seconds reaction time, the driver applies the brake. After the brake is applied, the car takes x divided by 24 seconds to stop. during which time the average speed of the car is x divided by 2 feet per second. If the car travels 165 feet from the time the driver saw the red light to the time it comes to a complete stop, which of the following equations can be used to find the value of x? And we have several quadratic equations in the bottom here. So what we want to, really, focus on here is assigning variables and also knowing one of the fundamental relationships in a lot of word problems, which is this. D equals RT. Distance is equal to rate times time. And so distance refers to, measures of distance, like feet or miles, or in this case, feet. Rate is equal to speed, so miles or feet per second, maybe. And time is equal to a unit of time, so seconds. And so this relationship is something that you can keep in mind, anytime, and you can manipulate it so that if you wanted to solve for t, you could divide by rate on both sides. You get t is equal to d divided by r. So this is a fundamental relationship that's important to keep in mind. And the next thing is saying, wow, there's a lot of information that's being thrown at us. I don't really know where to start, so let's just go from the beginning and then say, how do we want to do this? X is representing feet per second, so we know that x is rate, right? So rate is equal to x. And the driver sees a red light ahead, and after 1.5 seconds reaction time, the driver applies the brakes. So basically what we're saying is we want to we want to pick a term or a unit that we express everything in. And so for us, that should be distance, because that's going to give us the most, I think, common unit to work with in all stages of this problem. And we can break this problem down into several stages. The first stage is when he sees the red light and has a 1.5 second reaction time. We'll call that stage 1, right? The second stage is after he sees the red light and has a reaction time. So after stage 1, he applies the brakes, and that's going to be stage 2. And then at the end of stage 2 is when the brakes allow the car to fully come to a stop, and that's the end of the motion, right? So if we can find equations to represent both stage 1 and stage 2 of how far the car traveled, that's going to be the best way to solve this. And the reason we want us to do this in terms of how far the car traveled is because in this last line, we're given this information that in total, between stages 1 and 2, the car traveled 165 feet from the time the driver saw the red light right here to the time it comes to a complete stop right here, right? So with that total distance in mind, we know that if we can come up with the equations in the middle of this, then we can set that equal to 165, and that will give us the right answer. So this is equal to 165 feet. Okay, so then let's do this, right? So stage 1, which is representing the time of the distance the car traveled between the time that the driver saw the red light and actually pushed on the brakes. So we have our basic equation here. Distance is equal to rate times time. So how long did it take the drive? How long did phase 1 last, right? Or part 1 last? And it lasted 1.5 seconds because that's how long it took the driver to react. Okay, so we have 1.5. So distance in part 1 is equal to 1.5 seconds times what? So we want the rate. So how fast was the car traveling in the time between seeing the red light and not pressing the brake? So if the driver saw the red light but didn't press on the brake, that means he's going the same speed he was going before he saw the red light, which is, as we know, x feet per second. So that means the car was traveling at x feet per second for 1.5 seconds in phase 1. So that's going to give us 1.5x. Okay, great. What's the next phase then? The next phase is phase 2, which says after the brake is pressed, so after D1, how far did the car travel between braking and coming to a stop? So again, we want to do, distance is equal to race times time. How long did it take the car to stop? It took the car x divided by 24 seconds. So we get x over 24. And then how fast was the car traveling in that time? And we get the average speed of the car is x over 2 feet per second after the brake is applied. So that's x over 2. And we can simplify this equation, and that's give us x squared divided by 48. And that is how far the car traveled in that second phase of this process. And so putting that together, we get d1 plus d2 is equal to the total distance between the driver seeing the red light and then stopping, and that's going to be equal to 165 feet. So we can add that together. We get x squared over 48 plus 1.5 x is equal to 165. And so in order to make this a little bit easier, maybe we want to multiply this on both sides by 48 so that we don't have this denominator. We can see that in the answer choices that were given, none of the options have an a equal to 1 over 48. So multiply everything by 48 and we get x squared plus 72x equal to 7,920. And so we can put this all on the one side, and we get x squared plus 72x minus 7,920 equal to 0. And then we can go to our answer choice and say which one of these answer choices makes the most sense or matches up with our answer. And that's going to be answer choice D. Okay. So again, here we see that the difficulty was not in finding or solving a quadratic. We aren't even asked to solve the quadratic. The difficulty is translating this pretty complex word problem, I would say, into the algebraic form so that we can mess around with the quadratic form, right? And so again, this concept of breaking down this question into its logical components, part 1 and part 2, using the distance equals rate times time equation so that we know the total distance traveled, and knowing that distance is what we want to be messing with or working with, because we have this 165 feet total given to us at the end. These are the things that you should be really focusing on and honing in on, because those are the kind of key concepts that are being tested in a question like this. Okay, so hopefully that makes sense. And we're going to move on to the next kind of period of questions. So after quadratics, another really commonly tested passport to advanced math question is going to be exponential functions. So we can take a look at the little blurb that College Board provides when we are talking about exponential functions. So we get some passport to advanced math questions ask you to build a function that models a given context. Exponential functions model situations in which a quantity is multiplied by a constant factor for each time period. An exponential function can be increasing with time, in which case it models exponential growth, or it can be decreasing with time, in which case it models exponential decay. And so, focusing on these ideas of exponential growth and exponential decay, we can, really see that more efficiently with graphs. And so, taking a look at the slide over here, we can see on the left side we have a model for or a graph for an exponential growth model, and on the right side we have a model for the exponential decay model, right, or graph for the exponential decay model. And so this is really easy to understand in terms of the kind of general equation for exponential functions. You're going to have y equals a times 1 plus r to the power of x for growth, and then for decay you're going to have y equals a times 1 minus r to the power of x for decay. And again, the main difference, as we can observe from these equations, is simply whether or not r is positive or negative. In that sense, the only format of the equation that you really need to remember is this one right here. We have a lot of variables that we're dealing with here. A is going to be a constant, and it's essentially saying what is your starting point in the first period of growth / decay, right? So the easiest way we can think about this is exponential growth model might be like a bank account, which earns you interest every year. A is going to represent how much money did you deposit in the bank account on the first year. And that's the original amount or initial amount that you're working with, sometimes called the principal amount. Then we have R, which is the most important factor, and that's the rate of either growth or decay. And again, we said if it's positive, it's going to be growth. If it's negative, it's going to be decay. And we are basically saying how much interest on our bank account are we earning every year. And then x is going to be our variable, and it represents time. And so as x increases, that means the number of time intervals that have passed is going up. And again, it is not required that x be expressed in any certain time period. It can be expressed in years, uh, semi-annual, semesters, quarters, even hours or seconds, right? So it just, you have to keep in mind, you make sure you know what kind of time unit you are using when you're working with exponential functions. And then other than that, it's just some questions might also just ask you to manipulate exponential functions rather than build models. But we'll see both of those examples in the following two examples. So this is going to be one of those model building questions, and it says, a researcher estimates that the population of a city is increasing at an annual rate of 0.6%. If the current population of the city is 80,000, which of the following expressions appropriately models the population of the city T years from now, according to the researcher's estimate? That's going to basically, ask us to input essentially these numbers into our existing standard exponential growth function, right? So we know it's an exponential growth function because it says that the population of a city is increasing, and that's going to imply growth. So we go back to our default format, and it's a times 1 plus r to the power of x. And so we say, what can we sub in here? Like, what do we know in this question? So let's start with A. Do we know what the first, in terms of population, what is the initial population of the city in the year 0? And that's going to be given us here. If the current population of the city is 80,000, that means right now, in the starting period, the population is 80,000. So we get A is equal to 80,000. And then 1 plus, do we have a rate? We do. A researcher estimates that the population is increasing at an annual rate of 0.6%. So that's going to be equal to 0.006. And then do we have a time period that we're working with? And we do. It's modeling of the population of the city T years from now. So we can write in T at the top. And this is going to be our equation to represent the situation. And we see that matches up with answer choice A. And so again, for this question, I would recommend always writing out the equation yourself before looking at the answer choices. And the reason for that is because typically there's going to be answer choices that are pretty close, like two answer choices that are almost so there'll be two answer choices that are just completely wrong, right? Like it's very unlikely that you would choose those answers. And then there's going to be the right answer choice left, and then the almost right answer choice. And so what the trick with these questions is, if you look and you scan through the answer choices before writing out the equation, then you risk getting tripped up by that one answer that is almost right but not quite right, right? And so for us, that would be answer choice B, which is 80,000 times 1 plus 0.006 to the power of t, except t is on the inside of the parentheses instead of the outside. And so in that sense, if we had done what we do here, which is write it out for ourselves and then just look for the right answer among the answer choices, that's going to prevent us from being tripped up by any, almost right answer that College Board might be including in the multiple choice section. And so we can take a look at the other answer choices. We said here, but exponent's in the wrong place. For this one, they multiplied out the 80,000 into the parentheses, even though the exponent is raised to both of these, so that's not allowed. And then we have 80,000 times 0.006 t, where we just forget the 1 for some reason, right? So again, these are all things that we want to be on the lookout for. Okay, but hopefully we can see here, this is not a calculation-based question. It is not difficult in terms of the math. It is just translating or applying the knowledge given to us in these word problems into the format that we already know exists. Okay. And we can do a next question, and this is more of a manipulating the equation question type of question, and it says, which of the following is equivalent to this format? So 1 divided by the square root of x to the power of n. And so we can do a couple things with this. The first thing we can do is say, okay, well, how do we get this into one of these formats? And we can say we want, in all of these formats, x is, in the numerator position. It's not in the denominator. So what is 1 over square root of x really equal? And so we know two things. We know that 1 over x is equal to x to the power of -1. And we also know that square root of x is equal to x to the power of 1/2, right? And so these are kind of just basic exponent and radical rules. And so putting this information together, we can say 1 over square root of x equal to 1 over x to the power of 1/2 is equal to x to the power of -1/2. And, are we done here? No, we still have this n exponent, x to the power of -1/2 n, and this is just testing our knowledge of exponent rules. So what do we do when we have n on the outside and then an exponent on the inside? The answer is we can simply multiply them, so we get x is equal to -n/2, and that's going to give us answer choice B, right? So again, this is more of a question that is testing how comfortable we are with exponents, exponent rules, dealing with those simplification rules. And so if this is something that you feel like you want to work on, again, just refresh yourself on the different ways in which we can draw equivalent terms, like 1 over x is equal to x to the power of -1, or square root of x is equal to x to the power of 1/2. Okay, I think that basically covers the general gist of exponential functions. Another type of question you might see is going to be rational equations. So we'll take a look at this little blurb here. So we can see here, it says, questions on the SAT math test may assess your ability to work with rational expressions, including fractions with a variable in the denominator. This may include finding the solution to a rational equation. And a rational equation is an equation containing at least one fraction whose numerator and denominators are polynomials. And a common way to solve these questions is to reduce the fractions to a common denominator and then solve the equality of the numerators. I think this is going to be something that you will see less often on the SAT math test. It's not going to be the majority of questions, but it is important to know the method by which we would approach these questions. And again, that's kind of touched upon here. It essentially comes down to, most often, you would reduce the fractions to a common denominator, so you're just left with the numerator terms, and then you can, solve through the numerator terms there. Why don't we do an example to kind of illustrate what that would look like? So we have 3 divided by t plus 1 is equal to 2 divided by t plus 3 plus 1 over 4. If t is a solution to the given equation and t is greater than 0, what is the value of t? And for this, again, this is a rational equation. We have variables in the denominator. And so we want to basically say, what is a common denominator for all of these terms, right? So that we can work with everything in the numerator. Because as it is right now, this is terrible to work with, right? So one thing we could do is say, okay, well, common denominator of t plus 1 and t plus 3 and 4 is going to be 4t plus 1, t plus 3. Whoops. Sorry, I'm not sure what's going on here. Let's try that again. Try this one more time. Here we go, t plus 3. And that's going to be a common denominator for all of these fractions. So we can multiply each of these, each side by this fraction, by this term, and that will allow the equation to remain equivalent and allow us to kind of get rid of some of these weird fractions, right? So let's try that. So we have 4t plus 1 times t plus 3. Multiply that by 3 divided by t plus 1. So we get 4t plus 1, t plus 3 times 3 over t plus 1. So what we can do here is we can eliminate t plus 1 from here, and then we get 12t plus 3 12t plus 3, right? And so that's going to be what's left on that side. Okay, so let's do the left side here. So we do, again, the same term on both sides, 4t plus 1, t plus 3. Let's do t, 2 over t plus 3 first. So 2 over t plus 3. And we get that eliminated, and we get 8t plus 1. And then we have 1/4, which is just going to give us times 1/4, and that's going to give us t plus 1. So our final equation is going to look something like this. We're going to have 12, let me see where I can write this, 12t plus 3 equal to 8t plus 1, and then plus t plus 1 times t plus 3, right? And so if we simplify that, we can do 12t plus 36 is equal to 8t plus 8 plus t squared plus 4t plus 3. And then we want to put this all together. We have t squared on one side, so we get t squared. We want to combine all the t's, so we have 4t plus 8t is 12t, minus 12t is equal to 0, so plus 0. We have 8 plus 3 is 11, minus 36 is equal to negative 25. So we get t squared minus 25 equals 0, and then that's going to be our final equation. And so again, we have difference in squares here, and therefore we can simplify this one more step to t plus 5 times t minus 5 equal to 0. And then if t is a solution to a given equation as t is greater than 0, we know that t is equal to 5, because it can't be negative 5, because negative 5 is less than 0. So that's going to be our final answer for this equation. Again, this is not going to be the most common type of question. It is quite time consuming. Rational equations are a little bit more difficult, but you see here that no matter what the process might look like, we can solve this equation by doing the same approach, which is find a common denominator, multiply each side by it, simplify so that all the denominators are the same, and then solve for the equations. It is time consuming, and it's going to be a little bit of a hassle to do, but at the end of the day, that's going to be a process you're going to have to go through in order to get the right answer here. And we can do the same thing for any rational equation that we come across. The approach is going to work for those as well. Okay. The next type of question that you might see is systems of equations. So questions on the SAT math test may ask you to solve a system of equations in two variables in which one equation is linear and the other equation is quadratic, or another nonlinear equation. And so again, this is basically an evolution or a step up from some of the heart of algebra questions we were dealing with, because as you might remember, in heart of algebra, we had systems of equations where both equations were linear. We were solving those by doing substitution, elimination, sometimes graphing. And so we want to see here is what changes when one of those equations is linear and the other equation is now quadratic. And that's going to be seen in this practice question here. And the question is, what changes here, right? So we have 3x plus y is equal to negative 3, x plus 1 squared minus 4x plus 1 minus 6 equal to y. If xy is a solution to the systems of equations above and y is greater than 0, what is the value of y? And so what we can do here is, still do the exact same approach that we would do in a conventional systems of equation approach. In this sense that substitution is going to still work. We have 3x plus y is equal to negative 3. It's fairly easy to isolate y there. Y is going to be equal to, negative 3x minus 3. And so we can substitute that into the bottom equation, and we get x plus 1 squared minus 4x plus 1 minus 6 equal to negative 3x plus 1, right? That's the simplified form of this, right? And so what we see here is that we can actually keep this in a fairly simple form in which it's going to save us a lot of time. And that's by saying instead of multiplying or doing FOIL for x plus 1 squared and negative 4x plus 1, what we can do is keep x plus 1 in all the parentheses because x plus 1 is a common term in all of these formats. If we treat x plus 1 as a single variable and we don't split it up, then we actually end up with a quadratic that is fairly similar to a ax squared plus bx plus c format. And so we can see here that we just add, we get everything onto one side. So we still have x plus 1 squared here. We're not simplifying that. Now, instead of having negative 4, we're going to have negative 1 x plus 1, which says negative x plus 1, right? Because we're adding negative 3x plus 1 from both sides. And we have negative 6 here is equal to 0. We essentially treat x plus 1 as x, right? And so we say, okay, well, how can we factor this given that a is equal to 1, b is equal to negative 1, and c is equal to negative 6? So we still do our little square here. We say negative 6, what can we do? We want it to be negative on the b, so 1 times negative 3 is negative 3, 1 times 2 is 2, negative 3 plus 2 is negative 1, and so b is our negative 1 exponent. So we get x plus 1 times 1 plus 2, right? That's our first term, and we get x plus 1 minus 3 as our second term. And we can simplify this further into x plus 3 and x minus 2 equal to 0, and x equals either negative 3 or x equals 2. So what is the value of y? We want to plug this in and see which one is going to give us a positive y, because that's a requirement. So 3 times negative 3 plus y equals negative 3. We get y equal to 6. That seems to work. Let's check the other one. 3 times 2 plus y equals negative 3. Y is equal to negative 9. That's not going to work. So y equals 6 is going to be our final answer here. Okay, so again, we treat this the same as a regular systems of equations. We still go about using the substitution approach, and we see that there's also an opportunity here to simplify our work by keeping the term x plus 1 in the quadratic form rather than multiplying it out. Again, is that required? No. Is it possible to multiply it all out and still get the right answer? Definitely. And this is again just one of those shortcuts. If you notice that you can do this, it's going to save you a ton of time in terms of the amount of work that you're doing on this question. Okay, hopefully that makes sense, and we can move on to the next question. So the next set of questions is graphical representations of functions. This is again talking about the relationship between some equations and their graphical forms. And so we can take a look at this little blurb that's coming from College Board again. So we say a function f has a graph in the xy plane, which is the graph of the equation y equals f of x, or equivalently, consists of all ordered pairs x, comma, f of x. Some passports advanced math questions assess your ability to relate properties of the function f to properties of its graph and vice versa. You may be required to apply some of the following relationships. And it gives you this list: intercepts, domain and range, maximum and minimum values, increasing and decreasing behavior, and behavior in transformations. So we can go and look more specifically at what each of these little bullets is going to be asking us to do. And again, summarize things that you might have not reviewed in a little bit. So we start with the most basic, which is intercepts. So the x-intercept of a graph corresponds to the value of x such that f of x equals to 0, or in other words, where y equals 0. And this is visually seen as the point where the graph intersects with the x-axis. If the function has no zeros, then that means it has no x-intercepts. And so that's going to be visualized as something like this, right? So if you want to look at intercepts, pretend this is our graph. Let's just go by standard quadratic. So let's say anywhere that the quadratic intersects the x-axis, so it's right here and right here, those are two zeros, right? And those are what we refer to as x-intercepts. So anywhere the graph intersects the x-axis is going to be an x-intercept. The next kind of evolution, the flip side of that is the y-intercept. So the y-intercept of the graph of f corresponds to the value of f of 0, or where the graph intersects with the y-axis. If x equals to 0 is not in the domain of f, the graph of f has no y-intercept and vice versa. And so in that sense, that's going to be where the graph intersects the y-axis, and that's going to be right here for this graph, right? So, it's possible for both graphs to not have either an x-intercept or a y-intercept. For example, this graph here would not have a x-intercept because it never touches the x-axis, right? Or we can have another one like it never touches the x-axis. So that's just something to keep in mind. Okay, so the next thing we have is domain and range. So the domain is a set of all values of x for which f of x is defined, or basically exists. And so basically anywhere where f of x is not, DNE. The range of f is a set of all y such that y equal to f of x is equal to f of x for some value of x in the domain. So the domain and range can be found from the graph of f as a set of all x coordinates and y coordinates respectively of points on the graph. That's a lot of words. What does it really mean? Is it comes down to the range is saying how many values of y exist for this graph, right? So if we stay with this graph, the range is going to be anywhere between the low end, which is this lower vertex, where the graph never goes below this point, and that's going to be the lowest possible y value you can have, and then infinity, right? There's no line in which this graph of x, this parabola, does not continue to extend upward, right? It's going to continue to extend upward in both directions to infinity. So from this, let's say this is -2, from -2 to infinity is our range, right? That's all the possible y values that exist for this graph. Okay, so what else can we do with that? So the other one is the domain. And so domain is saying for how many values of x do there exist values on this function? And for this graph here, we would say -infinity on the left side, all the way to positive infinity. Domain is endless, right? It covers all the spectrum because there's not a single value on this parabola where you could plug in x and not get a valid function f of x output, right? And so that's going to be our domain. So those are just two concepts to understand. And then maximum minimum values are basically found by locating the highest and lowest points in the graphs respectively. Again, if we stick with the example of parabolas, then the maximum / minimum is going to be the vertex. So if it's a positive parabola, then it's a minimum. And therefore, this is the lowest point on the graph, and there's no point lower than it. If it's a negative parabola, then this is the highest point on the graph. There's no point higher than it. And so that's, again, just something to keep in mind when we're working with those graphs. Okay, and then we have another set of graphical kind of outcomes. The first one is increasing and decreasing behavior, essentially saying at which point over which intervals is the function increasing or decreasing. Again, we can do a parabola where we have a unique situation, not unique, but a situation where the graph is increasing all the way up to the vertex, at which point it stops increasing and starts to decrease. So increasing behavior from -infinity to 0, and then decreasing behavior from 0 to infinity, right? And so that's something to keep in mind for this graph. Again, that's just being able to identify those concepts. In terms of end behavior, the graph of f can indicate if f of x increases or decreases without limit as x increases or decreases without limit. So basically, what is happening to the graph as the function continues to increase? So for parabolas, as x continues to decrease, we know that the end behavior will be either negative or positive infinity because, there's no limit to where this is going to go. We could also have, other graphs like maybe exponential functions where as x whereas x is, come see if I can fix this as well. So we can have exponential functions where as x is here we go. So as x is exponential function, maybe a decay function that it approaches 0 as x increases to infinity, right? So it almost goes to 0, but it never quite touches. So there's a lot of different end behavior that you might see from graphs, and that's something that you want to keep in mind as well. And then finally, we have transformations. So for a graph of function f, a change of the form f of x plus a, where a is a constant, will result in a vertical shift of a unit of a units, and a change of the form f of x plus a with x plus a in the parentheses will result in a horizontal shift of units. So we can again deal with this with a parabola. So let's say f of x is equal to x squared. Our graph looks like this, right? And so let's say we want this to shift vertically. So we want it to go up. So we would do, x squared plus 4, and that's going to shift our graph upward. It'll go up here, and that'll be an increase from 0 to 4. If we wanted to horizontally shift, we might say x plus 4 squared with x plus 4 in the middle, and that's going to give us a horizontal shift to the left. Something like this, right, where you shift leftward by 4 units. Let's say you want to combine it. Maybe you do x plus 4 squared plus 4. Then you would do something like a leftward shift from the vertex and then a positive shift, something like that, right, where you shift it both to the left and vertically to upward. And so these are all kind of different ways in which you might see a transformation happening based on the modifications you are making to the original formula of the function. Okay, so let's take a look at some of the questions we might see. So a graph of which of the following functions in the xy plane has x-intercept at -4 and 5. So this is basically saying, do you know the basic definition of a 0 or a root? So if we know that the x-intercepts are at -4 and 5, that means those are the zeros, and therefore we can connect that with information we had about our quadratic function format and say if the zeros are -4 and 5, then the roots are x plus 4 and x minus 5, right? That means that when graphed, this graph will intersect the x-axis at -4 right here and positive 5 right here. And that's what this information tells us. This is basically saying, do you know the relationship between the function equation and the function's graph? And if we do, then that should be a very straightforward question. The next question we have gives us a graph and says the function f of x equals x to the power 4 minus 2.4x squared is graphed in the xy plane, where y equals f of x as shown above. If k is a constant such that the equation f of x equal to k has 4 solutions, which of the following could be the value of k? And so, when we talk about this, what we're really dealing with is saying, do we know what this line, if k is a constant, implies? If k is a constant and f of x equals to k, that means that k is a horizontal line. It's a straight line. It's a straight line that you draw across this graph. And what does it mean for this equation to have 4 solutions? It means that when we draw this horizontal line across the graph, we should see 4 distinct points at which the two lines intersect, right? Because a solution is essentially where the two lines are intersecting in this system of equations, right? So we can say, okay, well, let's try this out. So if a equals to 1, if k equals to 1, that means you draw a line horizontally at x equals 1, y equals 1, and we see that there are 2 unique solutions here, right? One over here, a little bit less than -2, another one over here, a little bit more than -1, right? And that's not going to work because we want 4 solutions, but we only get 2. So let's stretch that out. If we draw a line at at y equals 0, we get 3 points of intersection, which is 1 less than our 4, so that doesn't work. At -1, we can draw this line here, and we get 4 points. We get 1, 2, 3, 4. And that's 4 solutions where we both intersect. So that theoretically should work as a possible solution of k. And the last line, -2, is going to completely miss the entire graph. Doesn't even touch a single time. And so that's going to not be the case because that would have 0 solutions. So the correct answer would be -1. We draw that again. 4 unique points of intersection. And that is going to give us the correct answer as C. So the concept being tested here again is just understanding what are the implications of certain graphical relationships and what does it mean when we say there are solutions when two graphs are plotted together. If we know those concepts, then those should be straightforward as well. You know, the next kind of category of questions you might see in advanced passport to advanced math is function notation. So the SAT math test assesses your understanding of function notation. You must be able to evaluate a function given the rule that defines it, and if the function describes a context, you may need to interpret the value of the function in the context. So what we want to know here is essentially, do we know how to work with different equations, maybe composite functions? Do we know how to work with the definition of a function, which is that for every value of x, there's only a single value of y. That's going to be referring to what we call the vertical line test. There should never be a function where I could draw a vertical line and intersect multiple points on the function. This is not a function by definition because there are multiple y points for a single x. So these are kind of the questions that we'll see in function notation. With this question here, what we're working with is composite functions. So given two functions, g of x and f of x, and this relationship between the two, what do we know? What can we find? So the question says, if g of x is equal to 2x plus 1, and f of x is equal to g of x plus 4, what is f of 2? So there are several ways. There are two ways we can really solve this. The first one is we can combine these functions. So if we know that f of x is equal to g of x plus 4, we can substitute g of x in, so we get 2x plus 1 plus 4, and that's going to give us 2x plus 5. And then f of x, if we can only have, this one function, now it's no longer a composite, it's a single function, we can plug that in. We get 2 times 2 plus 5 equals 9, so we get 9. And that's f of 2. So that's one way we can solve it. The other way we can solve it is recognizing the relationship between the two. We can say if f of 2, if x equals 2, then that means for g of x, x is also equal to 2. So we plug in 2 here, we get g of 2 equals to 2 times 2 plus 1 is equal to 5. And then we plug in that output into f of 2 is equal to g of 2 plus 4. G of 2 we just got us 5, so 5 plus 4 equal to 9. So we see 9, solution, no matter what approach we take, is going to be 9 for both approaches. The thing that we want to keep in mind is that the initial approach of combining the composite functions into a single function is going to be more ubiquitous. What I mean by that is, the work might be similar in terms of finding just f of 2, but for this, if a different question wanted us to find f of 3, we could plug that in easily. We get 11. If it wanted us to find f of 10, we could plug that in and we get 25. So this is going to be a lot easier to use in terms of multiple situations, whereas this approach is only going to be efficient for just a one-time approach. It's not going to be efficient if we suddenly just change this number somehow. So I would probably recommend the solving the composite functions first before going through the motions of plugging in one by one. Hopefully that makes sense. And then the last category of questions we might see is something we see referred to as complex equations in context. So the SAT explains, or College Board explains this as, passport to advanced math questions may ask you to identify connections between the function, its graph, and the context it describes. You may be asked to use an equation describing a context to determine how a change in one quantity affects another quantity. You may also be asked to manipulate an equation to isolate a question of quantity of interest on one side of the equation. You may be asked to produce or identify a form of an equation that reveals new information about the context it represents or about the graphical representation of the equation. So this is where we're going to see a lot more of the applied kind of type of questions. And we just want to, keep, this is kind of a broad category of questions, and it's not going to be solving heavy. It's really more so how comfortable are we, applying the knowledge that we have to explain certain equations or identify relationships or model different situations. So taking a look at this is going to give us a better sense of what these questions look like. So the question here says, for a certain reservoir, the function f gives the water level f of n to the nearest whole percent of capacity on the nth day of 2016. Which of the following is the best interpretation of f of 37 is equal to 70? So basically, we're given the function in the relationships and we're asked to interpret a situation. So let's interpret it. So in this situation, we know that n is equal to 37 and f of n is equal to 70. So what does n represent normally? So the question says the nearest whole percent of capacity on the nth day of 2016. So if n equals to 37, then that must mean that this is the 37th day of 2016. The other piece of information we're given is that f of n is equal to 70. So what does f of n represent? Well, f of n, as given right here, says it represents the water level to the nearest whole percent of capacity. Put those two pieces of information together, and we get on the 37th day of 2016, the water reservoir is at 70% capacity. And that's basically what we're going to look for in terms of the answer choices. And when we look through those answer choices, we're going to see answer choice C is going to be the most, let me see if I can circle this. The answer choice C is going to be the most appropriate answer choice because that most closely represents what we predicted the question would be. So this is, again, one of those questions where we want to make sure we are, kind of predicting an answer and then matching it to the answer choices rather than reading it. We can take a look at the other answer choices and see whether they're wrong. The question choice A says the water level of the reservoir was at 37% capacity for 70 days. Two errors. First, it flips the number. 70 represents the percentage, not the number of days. And second, it's not the cumulative 70 days, but simply the snapshot picture on the nth day, which would be day 37. So that's not right. And so A and B would both be wrong. And then D says on the 70th day instead of the 37th day, and it says 37% capacity instead of 70% capacity. So again, just making sure we are keeping an eye on what we predict the answer choices to be. If we do that, we should be fine when it comes to these questions. So the next question says, if an object of mass m is moving at speed v, the object's kinetic energy is given by the equation Ke is equal to 1/2 m times v squared. If the mass of the object is halved and its speed is doubled, how does the kinetic energy change? I want to preface this by, these questions which give you scenarios require no background knowledge. So this is a physics equation, but it requires no knowledge of physics, right? It's simply saying how comfortable are you manipulating variables when you're told what they represent. So really, it's just an algebraic equation. Okay, so let's represent this. So in our equation, we're given that we're given that Ke is equal to 1/2 times mass v squared. If the mass, so then the question is, what does it change? So if the mass of the object is halved, that means m becomes m/2. And its speed is doubled. Well, speed is represented by v, so v is equal to, not v is equal to, but v becomes 2v. Now we just want to substitute this back in. So we get kinetic energy after the change is equal to 1/2 m/2 2v squared. So let's simplify that. We get m/4 is equal to 4, sorry, m/4 is multiplied by 4v squared. 4's cancel out. We get mv squared. What is the relationship between mv squared and 1/2 mv squared? This is 2 times the original kinetic energy. So we want to say, we would predict that kinetic energy is twice as large after this change than it was before. And that's going to be validated by answer choice C. The kinetic energy is doubled. And again, the thing we're keeping in mind here is this required no background information whatsoever on figuring out what these variables represented, right? It is simply saying, how do we manipulate this? What are the changes? How do we solve it? What is the relationship between the two afterwards? That again is again something we want to keep in mind, that context is not having any bearing on our approach to this problem. This is going to be seen even more so by our next question. So the next question says, a gas in a container will escape through holes of microscopic size as long as the holes are larger than the gas molecules. This process is called effusion. If a gas of molar mass M1 effuses at a rate of R1 and a gas of molar mass M2 effuses at a rate of R2, then the following relationship holds. R1 over R2 is equal to the square root of M2 over M1. This is known as Graham's law. And the question says, which of the following correctly expresses M2 in terms of M1, R1, and R2? So when we read this question at the end, we should say, okay, well, scratch all of this, right? Like we don't need to know anything about this, what each variable represents. We aren't even asked to manipulate these in any ways except just rearrange this equation. We don't have, you have to know this is called Graham's law, right? So the question becomes, we're given this equation, how do we reorganize it so that M2 is on one side? That's something that should be very straightforward, and I promise you that if this was presented as a question in the format of here's your equation, solve for M2, you would have no trouble solving it, right? So that's how we should approach it. What do we do when M2, well, to get M2 by itself, we square both sides, so we get M2 over M1 is equal to R1 squared over R2 squared. We square root of both sides, and then we multiply by M1. So M2 is equal to M1 R1 squared divided by R2 squared. And that should be our final answer. And so that's going to be answer choice A, and that's what we see being the correct answer. Again, so the thing that we would take away from this is that we did not have to listen at all to any of the stuff we talk about, molar effusion, Graham's law, gases, microscopic size. None of that really matters in terms of solving this question because it's really a straightforward reorganize the equation question, right? So really brings into perspective what we mean by complex equations in context. So in context, it's just an equation that we're messing with. Okay, keep that in mind. And again, don't panic when you see a question presenting all this extra information that you've never seen before and you don't expect to see. I mean, we expect no knowledge of chemistry or physics or any other field of subject of study when we're doing these math questions on the SAT. Okay, and then this last question here is going to help us understand, again, a modeling sort of approach, which is saying how comfortable are we dealing with contexts and manipulating them into different forms. So the question says, a store manager estimates that if a video game is sold at a price of $P, the store will have weekly revenue in dollars of Rp equal to -4p squared plus 200p from the sale of the video games. Which of the following equivalent forms of Rp shows as constants or coefficients the maximum possible weekly revenue and the price that results in the maximum revenue? So basically saying, looking at this question, we're looking for the maximum possible weekly revenue and the price that results in the maximum revenue. And this is going to be in the form of a parabola. What we're looking for is the vertex point, right? And so if we can put this into vertex form, then we'll have the final answer to the question. So remember, one of our equations that you might have seen before in math class is the calculation for the x variable, or in this case, the p variable at the vertex. And that's going to be given by, if we represent that p variable as h, we get h is equal to negative b over 2a. Here we can see that b is equal to 200, so we get negative 200 divided by 2 times -4. And our final answer is going to be equal to 25, right? So what that tells us is that the price that results in the maximum revenue is 25. Okay, so then what is the maximum possible weekly revenue? Well, that's simple. We plug that in to our equation, -4p squared plus 200p. We get -4, 25 squared plus 200 times 25. And let's calculate that out, and we should get equal to 2,500, right? And so in that sense, we should be left with our 2 points, 25, comma, 2,500. And then if we put this into vertex form, we would expect it to look something like this. RP equal to A times P minus 25 squared plus 2500. And that's a vertex form of our equation where we don't know what A is, but we're not asked to find what A is because we're simply saying which of the following equivalent forms shows as constants or coefficients the vertex points. And that's going to be this question paired up with answer choice D, where A is equal to -4 because we have P minus 25 and 2500, and none of the other answer choices give us those values, right? So this is kind of that process. Again, the thing we really needed, the key to understanding this question was being able to find the vertex points, the x and y coordinates. So we can do that by using this equation, h is equal to -b over 2a. It's possible you could have also done that by graphing it. Whatever the case, just knowing that you're able to find those solutions by doing that approach is going to be important for doing that type of question. Hopefully that makes sense. And that'll wrap up kind of what we talked about today in terms of the overall trend of Passport to Advanced Math questions. So those are going to be what most students are going to find to be the most difficult types of questions. And hopefully today the topics that we covered gives you an idea of the broad or the array of subcategories of advanced questions you might expect to see. Looking back on those questions, we can highlight a few of the most commonly tested ones. So we started with kind of rewriting expressions. I wouldn't expect to see a bulk of questions to look like that. I would expect quadratic functions to be heavily, heavily tested. And so knowing these 4 methods and tools for solving those questions is going to be extremely important when it comes to tackling those types of questions on the exam. The next thing we talked about was exponential functions. I would expect to see a few of these questions on the exam. They are going to be more of the modeling type of question, I would assume, where you're given a situation and asked to identify the correct equation that models it. I would expect to see a few rational equation questions maybe. Again, these are typically calculation heavy, but are going to really test how comfortable you are with the general approach of solving for the denominators and the numerators. We have the next kind of systems of equations approach. You may or may not see these questions. Just remember that it's fairly similar to the algebraic approach that we did in Heart of Algebra for linear equations. We have graphical representations of functions. This is something I would make sure you understand the different little segments for. And then we have function notation and complex equation in context. And I would expect to see a fair number of complex equations and context questions because that is something that College Board is really focusing on and asking students to truly understand not just the math, but also how to apply that math to more broad kind of questions with a wide range of things going on or moving parts. The last thing I want to end on is test taking strategy. So ideally, we want to go into this test thinking that we can cover all of the questions and have time to attempt all of them and even double check our work. Sometimes that's just not going to be possible. If it's very difficult or there's just not enough time to really build that expertise in these questions. And you might feel that when you go into a test, you basically know that you're not going to have time to get to all the questions. That's totally okay, and that's a situation that a lot of students are going to run into. And so this kind of 2-pass approach to the test is going to allow you to maximize your question, your score basically on the test. If you know that time management is one of those things that you struggle with. The first thing we have to remember is on the SAT, each question is weighted equally. It doesn't matter if it's a Heart of Algebra question or a Passport to Advanced Math question. It doesn't matter if it's a question that would be like a difficulty level 5 or a question that's a gimme like a difficulty level 1. Each question is weighted the same. So you get no bonus points for spending time on those hard questions relative to the easy questions. So in that sense, the goal of our strategy is to make sure if there's a question that you are comfortable getting with, and it isn't going to take you that long time, that you can nail those questions down before attempting the hard questions that you don't really know how to do. So that's why we do this 2-pass approach, where a pass is simply one round through the test. Pass 1, you're picking the lowest hanging fruit. And it's basically saying, you're reading the questions and you're saying, is this a question that I'm comfortable solving? And is the question that I could solve fairly quickly? If I already know the steps I'm going to take, go ahead and solve it. And those are going to be the questions that you feel are the easiest for you. And that, I wouldn't recommend spending more than a minute or so on any of these questions. If it's taking a long time or you realize, this is a lot harder than you thought, just come back to it and kind of follow up on what you did. The point for this first pass is to end the test with a significant amount of time left. And it's okay to have questions where you're unsure what the answer is at that point. You just want to knock out all the questions where you know how to do them and you get them right. The second pass then is going to be after you finish that first pass and you've read all the questions, and you say, okay, well, let's go back. Let me pick my battles. And that means taking on the questions in ascending order of difficulty. Because again, you are not rewarded for getting the question that is the hardest on the test right. That's just 1 point, just as the easiest question is also 1 point. So go and identify those questions where maybe you were already halfway through and you just needed a little bit more time, or a question where you know how to do it, you just didn't feel like you wanted to spend the time on it right then. Do those questions first and then go on to tackle the questions where you are less and less sure of what you want to do there. So that's going to be our two-pass approach. And then the second thing we want to keep in mind is just the general format of SAT exams. In terms of structure, we have multiple choice and gridding questions on both non-calculator and calculator sections. And what we want to remember for that is that a lot of times, you might think that a multiple choice question would be easier because it is, giving you options and you have a 25% chance of guessing it right. But the problem with that is that, actually the first few gridding questions are actually normally fairly easy. And so if you're getting to that point in time where you're having to choose between questions you want to attempt, it actually might be better to give a shot at the first few gridding questions rather than restricting yourself to just the multiple choice questions, especially the last few, which are typically the hardest ones. And finally, remember that College Board does not penalize you for guessing on a question. You have no incentive to leave a question blank. You lose no points for getting a wrong answer. So if you make sure that you guess for every question, that is also a way in which you can ensure that you might get some free points back that you might not have gotten otherwise if you had left them blank. So I would just pick a letter and say, I'm going to put C for every question I end up leaving blank or end up not knowing how to do, and kind of have that be your test day approach. Okay, so hopefully that made sense, and that covers basically everything we wanted to go over today. If you guys have any questions, feel free to book sessions with OneClass tutors. And other than that, I hope everybody's staying safe and wishing you guys all the best and good luck on your studies. Take care, guys, and have a good rest of the week.